Hi guys, I will cover today doubly reinforced beams, and this type of cross section has both tension and compression reinforcement. Both of them are used in the beam, and that's the reason why we consider this type of cross section as doubly reinforced beam. Usually we having this type of cross sections or this type of beams when beam is having negative bending region and in the mid-span region of beam or beam which is heavily loaded in which deflection needs to be in control. So we have cross-section B as width, H as a height. At the bottom the bottom cross-section has tension steel and the top has compression steel. So the reason why we are using doubly reinforced concrete beam, firstly, it will reduce sustained load deflection. Then we will have increased ductility and we will have change in mode of failure from compression to tension and also fabrication easy. So stress strain diagram for doubly reinforced concrete beam is again based on witness block, but in comparison to singly reinforced concrete beams, we will have one additional force which will come from steel in compression. So we need to have equilibrium that both forces in compression, one from concrete, the other one from steel, are equal to tension force, which will be due to steel or area steel in tension region. So this will be double reinforced section. Here is a strain distribution. Then we have internal forces and the analysis of nominal moment strength for doubly reinforced concrete. Here, it is not ideal to assume that compression steel strain exceeds the yielding strain. So using similar angle triangle theory, we can compute the strain in compression steel. So we will have epsilon s prime. So again, using the similarity of triangles and using the strain for concrete to be 0.003. D prime will be the concrete cover for top fiber of cross section, and we will have C as a depth or location of neutral axis. So epsilon S prime, which belongs to steel in compression, will be C minus D prime over C times strain in concrete. Similarly, for witness block, we need to compute location C or A, and we need to satisfy the equilibrium. So for doubly reinforced concrete beam, neutral axis can be computed using trial and error method. And what we have here is that we are assuming for doubly reinforced concrete that location of neutral axis is somewhere between d over 4 and up to d over 3. So in that range, we need to determine the location of neutral axis. So again, we have equilibrium condition, and instead of compressive force in concrete, we can use 0.85. Fc prime is compressive strength of concrete. We have width of cross section. A is the depth of witness block plus AS prime, which will be area of steel in compression, times Fs prime, again, that is a stress which belongs to a steel in compression, minus 0.85 times compressive strength of concrete. And we have minus AS times Fu, which is area of steel in tension, times yielding stress, and that will give us total tensile force. So the equilibrium needs to be satisfied, and using moment equilibrium condition, we will obtain that moment strength capacity is compressive force C, which is here, times the depth minus half of a witness block plus force in compression from steel times the depth of the cross section minus concrete cover in compression zone. So only in this way we can determine compressive strength of concrete. And here we have some steps which we will follow in order to determine the moment strength capacity of doubly reinforced concrete section. So we have firstly to assume that strain is higher or equal yielding strain, that stress of steel is equal yielding stress, which is 60 ksi. Then we need to assume the value of C. We are calculating epsilon S prime. And after that, we are going to step number 4, where is Fs prime, which is a stress for steel in compression using to Hooke's law. We have modulus of elasticity of steel times strain of steel in compression zone. Then we are calculating the forces, and we have to check the equilibrium condition. If two forces in compression are equal T, if this equation is not satisfied and we have compression forces higher than tensile force, we need to decrease the value of neutral axis. If we have compression forces to be less than tensile force, we need to increase the value of location of neutral axis, and after that to compute the nominal strength capacity. Here is one example of doubly reinforced concrete beam. So we have 3 rebars in compression zone, 6 rebars in tensile zone. The width of the cross section is 12. We have a height which is 20. Concrete cover for a compression rebar is 2.5 inch. And here, since that we have 2 rows, the centroid is determined to be 3.2, which means that our depth of cross section is 16.8. So compressive strength of concrete is given to be 4,000 psi. Modulus of elasticity of steel is 29,000 ksi. We have we need to compute nominal moment strength of given beam. So firstly, we need to use to assume that strain in steel is higher or equal yielding strain, and that stress of steel is equal yielding stress, which is 60 ksi. Then we are assuming the value of C. We said d over 4 up to d third, which is 16.8 in our case, divided by 4 will give us 4.2 inch, and we have 16.8 divided by 3 is 5.6, so we need to pick C between 4.2 and 5.6 inch. Let's use C to be 5. We are going in step 3. So we need to calculate the strain in compression steel. So epsilon S prime is equal strain in concrete 0.003. We assume C to be 5. We have concrete cover in compression zone 2.5, and we are dividing by 5. That will give us epsilon S prime to be 0.0015. The next step, Fs prime, will be calculated using Hooke's law. Instead of modulus of elasticity, we are plugging 29,000 ksi times 0.0015, which is 43.5 ksi, and that is less than yielding stress. Then we have to determine all forces. Forces from steel in compression will be As prime, which is 3 inch square, times Fs prime. We calculated this to be 43.5 minus 0.85 times Fc prime, which is 4. That is a compressive strength of concrete. And we obtained 120.3 kips for this force. The next force is a force from concrete, which is 0.85 times Fc prime, that is 4, times B, which is 12, and A is 0.85 times C, which is in our case 5. So this one will give us value of 173.4 kips, and tensile force will be As times yielding stress. So in this case, area of steel in tension region is 6 times 60. That will give me tensile force of 360 kips. The next step, we need to check equilibrium, and we have compression forces 293.4 tension is 360 kips, so we need to increase the value of C and to start with the step number 3 until the equilibrium condition is satisfied. So after that, we can use the Excel sheet for next iteration. And in this case, the location of neutral axis is obtained to be 6.19 inch. After that, we are using the equation for moment strength capacity, and in this case, we will obtain 427 kip feet. Phi will be 0.9 since that we have tension control zone, and our moment strength capacity is 384.002 kip feet. So with this, I will finish with the doubly reinforced concrete. And the next chapter, which I will cover, will be columns.